how do we know when the dinosaurs died? You can all read this cartoon. Those of you in the back, it says, oh crap, was that today? As Noah's Ark just sails away. So surprise twist ending to my presentation. That was it. Okay. Okay, so a little bit about myself. My background is based in planetary geology, which basically means I study the geology of other planets, which largely centers around impact craters. Impact craters you see on almost all of the rocky planets in the solar system, including on Earth. And they're really cool because they contribute a lot to planetary development, and they excavate huge amounts of material. They let us see what's under the surface of a planet. And on Earth we care because they have a huge impact on the development of life. In particular, we care how old these impact craters are, because say a really large space rock hits the Earth every 10 million years, and we're coming up on 9 million something since it happened, we're going to want to know that something's about to hit us again, right? So we care about how old these things are, how frequently they occur, things like that. The other major effect on development of life, of course, has to do with dinosaurs. So if we go back in time, 67 million years, there were adorable little dinosaurs wandering the face of the Earth. And then something happened, and they all died. It was very sad. They were fairly swiftly buried by sediments. And over time, these layers of sediment built up and up and up and turned into rock. And what that left us with was this rock record. So we have a series of rocks where there are no dinosaurs, and underneath that, we have a series of rocks where there are dinosaurs. Unsurprisingly, people have known that the dinosaurs were dead for many, many years. We also know that they died a long time ago because of how much rock they're buried under. And this transition layer between the dinosaurs, no dinosaurs rocks, it's called the Cretaceous-Paleogene boundary, or the KPG boundary, because it occurred at the end of the Cretaceous period and the beginning of the Paleogene period. And those are just words that geologists like to use to talk about times in the very distant past. So the KPG boundary is a real thing. It's not just an idea. If you know where to go, you can actually go and touch it. So this figure here is from Montana. And this thick, dark line, right there, is the KPG boundary. So we have dinosaurs, no dinosaurs. The closest one to here, as far as I'm aware, is actually in Denmark. So you can get a cheap flight from Edinburgh with Ryanair, go, take a train. You can go touch it, which I think is super, super cool, but I'm a nerd, so. Okay, so people have known about this boundary for a long time. And in 1980, some scientists were studying it, and what they found was a huge amount of iridium. And iridium is an element that you typically don't find in Earth's crust, because when the planet was forming, it's quite heavy, and all of it sunk into the middle. Where you do find it is in asteroids and meteorites, basically things from space. So they found this iridium anomaly, spike of iridium, all across the Earth at the KPG boundary. And they thought to themselves, aha, maybe this is why all the dinosaurs died. Maybe there was some giant catastrophic impact event, and it wiped out the dinosaurs, as well as like 3/4 of the other life on Earth, but dinosaurs are a cool part. You can read about it in this book. This is a legitimate scientific book, which is really cool, despite the cover. So the search began for a crater of doom. Where is this massive crater that would have wiped out the dinosaurs? It's quite obviously right here in this photo, just off the Gulf of Mexico. In the Gulf of Mexico, I never know if I should say it's in the Gulf or on land. It's like half and half, but it's about 150 kilometers in diameter. And this is what it would have looked like at the time that it formed. An artist's rendering, not a photo. So currently, the entire impact structure is buried. And if you're interested in studying an impact structure, you need to get some rocks from it. Since this one is mostly underwater, how did we get the rocks? Well, a little over a year ago, a group called the International Ocean Discovery Program sent a boat to just off to just off the coast, and it put down these big poles and actually raised itself off the seabed and then drilled down 1.3 kilometers and recovered 800 meters of rocks like this. And so now that we have samples, we can figure out exactly when this impact crater formed. Because the thing is, when they were looking for the impact, they found ejected deposits, which is material that was thrown out of the crater and really far away, but stratigraphically associated. So it's in the same layer of rock as the impact crater. And they dated those, and they got an age that corresponded with the age of the Cretaceous-Paleogene boundary. But there are some people who say, okay, but we don't know for sure that those deposits from over there actually came from this impact crater. And they did some dating on this impact crater, but if you remember Ed's talk, it's not reproducible. So some people still like to argue that this impact was not the cause of that mass extinction. So we're looking at now new material from the crater to see if we can clarify the situation at all. But how do you figure out how old a rock is? To start with, all good explanations of science, I think, should involve radioactivity and candy. So how many of you have been eating the candy that's on your tables? Yeah, okay, very good. The candy wasn't radioactive. Heather said I wasn't allowed to do that. But it makes a good analogy. And the analogy is this. I put out those bowls of candy at 7 p.m. Well, slightly before, but so you guys could come in and just start eating. And when a rock is formed, it locks up an element called potassium, specifically potassium-40, which just means potassium that weighs 40 atomic mass units. And then, over time, much as your candy has turned into a pile of candy wrappers, some of the potassium will turn into argon. So that's some future time, let's say 8:15. And then, if an event happens to your rock, such as melting, okay? This happens during an impact. A lot of the rock melts, and since argon is a gas, it can escape from the liquid rock. It's basically lava. And I don't know, maybe somebody from your table cleaned up, chucked all the wrappers in the bin. And what this does is resets the clock. So for the candy clock, we start again because you guys are good citizens and throw out all your wrappers. And for the potassium-argon clock, it means all the argon is gone, and it will slowly start to accumulate again as the rock ages. So if you wanted to, we could figure out the half-life of candy and do a bunch of math to figure out how long we've all been sitting here, but that's not really the point of my presentation. So, okay, so what do we do to a rock to get this information out of it? First, we crush it. Then we wash it in acid. And then we pick out individual little grains. And after it's been through all that, people usually say, wow, you must really hate rocks. And I say, well, I like them enough to date them. Thank you. So now we have all these tiny little grains of rock. And the reason we pick them so carefully is to make sure that the rocks that we're selecting were actually formed during the impact event. And just to give you a scale, this is my finger, perfectly normal-sized finger. And this is what all of my sample preparation for months and several kilos of rocks has come down to. So then we'll take those little individual bits of rock and put them in a mass spectrometer. And the important thing that the mass spectrometer does is it will tell us how much potassium there is now and how much argon there is now. By adding those together, we can tell how much potassium we started with. And because we know how fast potassium turns into argon, we can figure out how long these elements have been locked up in a rock. And that will tell us the age of the rock. So for my project, we're redating tektites. So that's the material that landed way over there, but that's associated with the impact crater. These have been dated before and have given really, really nice ages. We're dating material from the KPG boundary, which has also been dated before and has given really, really nice ages. And then we're dating these new rocks from the impact crater itself. And what we anticipate is that all of these will end up being the same age, and we can say definitively that the impact event occurred at the same time as these other events. And then we can narrow down what was happening in the world around the time that this happened, and we can clarify the picture of mass extinctions and Earth's history. Thank you.